everyone, Chapter 2, Atomic Structure, 2.3 Electronic Configuration. What is the electronic configurations? It shows how the electrons are distributed among the various atomic orbitals. There are two methods to write the electronic configurations. First, by using the orbital diagram. For the example, we have the element oxygen with the proton number is 8. So it shows that the oxygen has 8 electrons. And to write the electronic configurations in orbital diagram, you have to draw the box. Okay, for the example, for the 1s and 2s, okay, label each of the box with the orbital, with the combinations of the n and l. Okay, for the example here, 1s, 2s, and for the 2p, there are 3 box combined together. Okay, because we have the px, py, and pz. So there are 3 box, and each box, it can occupy 2 electrons. And by using the arrow, upside down arrow, okay, you can fill, okay, the each box, okay, with the 2 electrons. Or you also can write in this way. Okay, you just write, draw the line, but label still same as above. Okay, which is you label with the 1s, okay, for the orbital 1s, and then 2s and 2p. Okay, but you have to make sure that the space, okay, between the 1s and 2s is quite larger compared to the line in orbital 2p. So orbital 2p, we know that it has px, py, and pz. So the space, okay, quite small compared to the space between 1s, 2s, and 2s and 2p. So here you can see that for the 2p, okay, it has 3 lines. And this is the example, okay, for the 3D. 3D, there are 5 orientations. -2, for the example, -2, -1, 0, +1, and +2. So it shows that for the orbital diagram, it has 5 boxes. Okay, there are 5 boxes, and you label it with the 3D. Okay, this is a how to write the electronic configuration by using the orbital diagram. And let's see the second method, SPDF notation. Okay, what is the SPDF notations? Okay, this is an example SPDF notation for the hydrogen atom, which is it only has 1 electron, and this is one is referring to the energy level or principal quantum number. So this is the principal quantum number, and this one, okay, S, it refers to the type of the orbital subshell. So you know that there are s orbital, p orbital, and d orbital. So here it can be orbital p, okay, or d. And then the superscript 1 here, okay, the number here, it refers to the number of electrons in the orbital. Let's say for the orbital s, the maximum number of electrons can occupy this orbital is 2. So if there are 2 electrons, it will become 1 s to the power of 2. Not to the power, actually, it is a superscript 2. Okay, alright. So let's see the example. Okay, by using the same elements, okay, oxygen, okay, with the proton number 8, and it shows that it has 8 electrons. So this is how write the SPDF notation for the electrons of the oxygen. So the number, okay, 1, 2, 2 here, okay. So that one is the principal quantum number. So at n equal to 1, okay, there are only one s orbital, and how many electrons can occupy in orbital in orbital s? The maximum is 2. Okay, because there are only one box. Okay, if you refer to this one, there are only one box, so it shows that it can occupy by 2 electrons only. So that's why here is 2. Okay, and then the green one, okay, this one is the azimuthal quantum number L, okay, the subshell. All right, so this one S, okay, and P. And superscript number, we refer to the number of electrons in the subshell. So this is how you write the electronic configurations by using the SPDF notations. Okay, but please keep in mind, okay, you need to know the degenerate orbitals. Okay, which one we call it as the degenerate orbitals? Degenerate orbitals, we refer to the orbital with the same energy. It is for the orbital P and D only. So because P, it has Px, Py, Pz, so electron occupy this orbital, okay, have the same energy. Same for the orbital 3D. Orbital 3D, there are 5 orientations, okay, and the orbital is 3D xy, 3D yz, 3D sz, 3D x square, y square, and 3D z square. And the electron that occupy in this orbital, okay, have same amount of the energy. So we call this orbital as the degenerate orbitals. Orbitals with the same energy. Okay, there are rules to fill the electrons in the atomic orbital. There are Aufbau principle, Pauli's exclusion principle, and Hund's rule. So these 3 rule, okay, is used to fill the electron in the orbitals. Let's see the Aufbau principle. So electrons fill the lowest energy orbital first and other orbital in order of increasing energy. So this is used how to write, okay, the electronic configuration, okay, to fill the electrons, okay, according to the increasing energy, which is at n equal to 1, there are only 1s here. N equal to 2, there are 2s and 2p. N equal to 3, there are 3s, 3p, and 3d. Okay, n equal to 4, actually it has until 4f, but normally for your syllabus, mostly you just need to write the electronic configuration that using until orbital d only. Okay, so no need to fill the electron in orbital f. So you just can write until d. Okay, actually this one as the guided, okay, for you to fill the electron in the orbital. And refer to this diagram, okay, you can see that the lowest orbital with the lowest energy, we refer to this one, okay, 1s. So 1s has lower energy than 2s, 2p, 3s, 3p, but here you can see that the 4s and 3d. Okay, if you see here, the 4s, okay, is lower compared to the 3d. So refer to this diagram, okay, 3d electron, it will fill the orbital 4s first, than 3D. Okay, so it shows that the 4S is lower energy compared to the 3D. Later on, I will explain why it happens. Okay, so next, okay, you can see that for P, okay, higher energy compared to the 3D, and same for the 5S. Alright, so it gives you the two example, okay, which is the first orbital diagram. It shows that it is wrong. Why? Because when you fill the electron in the orbital, you have to fill the electron to the maximum. So for the example 1s, the maximum electron can fill in the orbital s is 2 electron. So you have to complete the first orbital, okay, with the 2 electron by using the upside down electron, okay. And this one is wrong because the first the 1s orbital is not complete, okay, but it fill the next orbital with the 2s, and then the 2s orbital also not complete. Now, so this is wrong. All right, the correct one is this one. Okay, it fill the 1s orbital, okay, full to the maximum with the 2 electrons, and then the next electron it will fill in the 2s orbital. Okay, so this is an example. The element for the element with the 3 electrons. Okay, if you have more than that, for the example, okay, you can fill the orbital 2s, okay, full the 2 electrons, and the next electron will fill in the orbital 2p. So here I show you the animations, okay, by using this diagram of Aufbau principle, okay, which is alright. Next, this one is the relative energy level of the atomic orbitals. So this one, it shows it just like the energy profile diagram, but this one it relates to the energy level of the atomic orbital. So you can see that the lowest energy level is the 1s, okay, with the lowest principal quantum number is the lowest energy, followed by the 2s and 2p, and here you can see that the 4s slightly lower compared to the 3d. Okay, actually this one it relates to the characteristic of the electrons. Actually, electrons, we know that it is a negative charge, so maybe there will be repulsions, okay, between the electrons, so it makes the orbital 4s lower compared to the 3d. Okay, let's see the example. So these questions, okay, it asks which of the following pairs is lower in energy for the case of many electron atoms. So let's see for the 2s and 2p for the A. Okay, for the A, between 2s and 2p, so you can see that of course the 2p, okay, is larger than 2s. Okay, let's see B, 3p and 3d. So 3p and 3d. So okay, 3d higher energy than 3p. And let's see 3s and 4s. Okay, so clearly you can see that 4s larger than 3s. And then okay, D, 4d and 5f. Okay, 5f not listed here, but of course we know that it is higher compared to the 4d. So this one, 5f larger than 4d. Okay, and the last one, 3d and 4s. This is the one that you should alert and be careful. Okay, because between 4s and 3d, 3d is higher compared to the 4s. Okay, the question asks you which of the following pair is lower, so you also can answer like this, or you just answer the highest one, the lowest one. Okay, means that you can answer the one here. Alright, so next, okay, second rule, okay, to use, okay, in electronic configurations, writing the electronic configurations, is the Pauli exclusion principle. So it said that no two electrons in the same atom can have the same 4 quantum numbers. Remember, 4 quantum numbers, we have the principal quantum number, angular quantum numbers, magnetic quantum numbers, and also electron spin, right? Okay, so in other words, each of the electron must have a different set of the quantum numbers. For the example, it gives the helium atom with the 2 electrons, and in SPDF notation, it is 1s2. Okay, so by using the orbital diagram, if you fill the electron and you write the arrow just like this one, okay, it will show that the first electron and second electron will have same quantum numbers. Okay, so this is the combinations of the 4 quantum numbers. 1 for the N, first 0 for the L, second 0 for the M, and positive half is the spin. Okay, so these combinations for quantum numbers, just like the address of the electrons. Okay, so according to the Pauli exclusions, there is no 2 electrons in the same atom can have same 4 quantum numbers. But for the first example, both of the electron, it shows that the set of the 4 quantum numbers are same. So this is wrong. Okay, and the second one, okay, you can see that both of the electron, it shows that the arrow, it writes the arrow like this one. Okay, and then you can see that both of the arrow, it has the same set of the quantum numbers, so this is also wrong. Okay, and the last one, okay, actually you have to write the arrow upside down. Okay, and then you can see that the first 3 quantum numbers are same and equal to 1 for both of the electrons. L 0, M 0, but the difference is spin. Okay, one of the electron is positive half and the other one is negative half. So both of the electron in the same orbital have different set of the quantum numbers. So this one is correct. Okay, because it obeys the Pauli exclusion principle. Let's see the next or last rule. There is Hund's rule. Okay, Hund's rule said that the most stable arrangement of electrons in orbital of subshell is the one with the greatest number of parallel spin. And electrons, it will fill and all degenerate orbitals singly before they pairing up. So Hund's rule, it is used for the degenerate orbital, which is there are 2 types of the degenerate orbital, orbital P and orbital D. So for the example, it gives with the carbon with the proton number is 6, and it shows that the carbon has 6 electrons. When it write the electronic configuration in orbital diagram, you can see that in orbital 2s there are 2 electrons, 2s and also 2 electrons. And when to fill the orbital 2p, okay, it has to fill singly first. Means that you have to fill each box with the 1 electron. Okay, so for the example here, you cannot fill the first box with the 2 electrons. Okay, you have, because this is a degenerate orbital, so you have to fill singly first, because they are only balanced 2 electrons. So you need to fill the first box and second box with the single electrons. So this one we call it as a parallel spin. So this is more stable. Okay, that's why this writing, okay, is said that it obeys the Hund's rule. Okay, let's see the exercise 2. Which of the following is the correct orbital diagram for the ground state electron configuration for the nitrogen with the proton number is 7? It shows that it has 7 electrons. Okay, the first one, A. Okay, this one is not correct because you can see clearly here for the orbital 2s. Okay, the arrow is at the same way. Okay, so it is not correct because this arrangement, it shows that the electron, the 2 electrons has the same set of the quantum numbers. So this one is not obey. Okay, it not obey Pauli exclusions principle. Okay, so this is wrong. Next, let's see for the B. Okay, B, the arrangements of electron in orbital 1s is correct, 2s is correct, but okay, for the degenerate orbitals 2p, okay, this one is wrong. Why? Because the electron is fully filled in the first box. For the 2p, the degenerate orbital, you have to fill the electron singly first. Then, next, for the fourth electron, you have to pairing up. Okay, so okay, not obey the Hund's rule. Okay, next, okay, the last one. Okay, the last one, okay, this one is correct. Correct, so this one also correct. So for the C, okay, it's obey the Aufbau, okay, which is it fill the orbital, okay, 1s first, followed by 2s and 2p. So it fill the orbital in order of increasing energy, and it also obey the Pauli exclusion principle. So you can see that all the electron, especially for the 1s electron in the orbital 1s and orbital 2s, the arrow at the different side. And then for the Hund's rule, you can see in the orbital 2p, degenerate orbitals, okay, electron fill singly first, okay, and so C, okay, it obey all the 3 rules. Okay, let's see the example 2. Okay, write the electronic configuration for the potassium and magnesium. Okay, I show you for the potassium. It gives you the proton number 19. It shows that the potassium has 19 electrons. So by using this diagram, okay, by using this diagram, so the electronic configurations for the potassium is, okay, you will fill the orbital 1s first, 1 2s2, okay, 2 electrons, and then 2s2, okay, and then followed by 2p. The maximum electron can occupy in orbital 2p is a 6. So now you see that there are 2 to 6, so 10 electrons. Next, we need another 9 electron. Okay, the next electron it will fill in orbital 3s, and then after 3s, 3p, 6 electron. So now there are 10 plus 2 and 6, so there are 18 electrons. Another 1 electrons it will fill, okay, 3p. After 3p it will fill 4s, so 4s1. So this is the electronic configuration for the potassium by using the SPDF notation. If the question doesn't ask you the way to write the electronic configurations, so you just write in the SPDF notation form. Next, example 3. Okay, this one is the it needs you to write the electronic configuration for the ions. So it gives you all these ions, and then at the same time it gives you the proton number for the neutral elements, okay, for each elements. And let's see for the vanadium 5+. Okay, it gives you the proton number vanadium. Firstly, you have to write the electronic configuration for the neutral vanadium. Means that before it forms ion. So for the vanadium, it has electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. Okay, this arrangement is follow the Aufbau principle. But let's say if you want to write in the form, okay, you want to write like this one, 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, okay, and then followed by 4. Okay, it also can be accepted, but I prefer this one, okay, this one, because you fill the electron according to the Aufbau principle. Aufbau principle. So it's better to write like this one. Okay, and then when you write the electronic configuration for the neutral vanadium, to get the electronic configuration for the vanadium 5+, you have to remove, okay, 5+ means that you have to remove 5 electron, and you need to remove the 5 electron from the highest end. So the highest end in the electronic configuration for the vanadium is 4. Okay, so in orbital 4s there are 2 electrons, so you need to remove these 2 electrons. So you need to remove 5 electrons. So now you remove 2 electrons from the orbital 4s. You need another 3 electrons to remove, which is from the orbital 3d. Okay, so the electronic configurations for the V5+ is 1. Okay, next, let's see exercise 3. What are the possible quantum numbers for the last outermost electron in chlorine? So chlorine, we know that it has the proton number, okay, for the chlorine, with the proton number 17. So let's okay, first you have to write the electronic configuration for the chlorine, which is according to Aufbau principle. So 1s2, 2s2, 2p6. So there are 10 electrons, another 7 electron. Okay, 3s2, and 3p5. So this is the electronic configurations for the chlorine. So it needs you to write to give the possible quantum numbers. Possible quantum numbers, we refer to the combinations of the N, L, M, and S for the last outermost electron in chlorine. So for the last outermost electron in the chlorine, we refer to the electron in orbital 3p. So firstly, you have to write N, L, M, S, and it is equivalent to, which is the N, okay, because possible the last electron is occupied in orbital in principal quantum number n equal to 3, so n equal to 3. L, because it is p, so 1. M, the orientation for the p, it can be -1, 0, or +1. So you can take any this number. Alright, so for the example, I take +1, and then the spin, okay, either -½ or +½. So I use +½ So this is how you write the set of the quantum numbers, okay, or the other words, the address of electrons. Okay, however, there are anomalous electronic configurations, which is chromium and copper. Chromium and copper both have the electronic configuration which are inconsistent with the Aufbau principle. Okay, the anomalous are explained on the basis that fully filled or half-filled d orbital is more stable. So it using the fully filled d orbital and half-filled d orbital is more stable. For the example, chromium with the proton number 24. Then when you write the electronic configurations, okay, this is the expected electronic configuration. Actually, AR is it refers to the electronic configuration for the argon, okay, here, okay, and then followed by the 3d4 and 4s2. Actually, this one is the way to simplify the electronic configuration, but for you, okay, do not do like this one, okay, as a notes is okay. Okay, for you to write the answer, do not write like this one, okay. So for the observed or actual electronic configurations, actually it becomes 3d5 4s1. Before that it is 3d4 4s2, but because to achieve the stability of the half-filled d orbital, fully filled is 10 electrons, half-filled 5 electrons. So this arrangement of electrons is more stable compared to this one. This is the anomalous case for the chromium. And let's say for the copper, with the proton number 29 and it has 29 electrons, and you see that this is the electronic configuration for the expected electronic configuration for the copper. But you can see that the 3d9, it almost to achieve fully filled d orbital. So that's why the actual electronic configuration for the copper is 3d10 4s1. How it become like this one? Okay, let's see this one. For the chromium, expected electronic configuration, this one, okay, 3d4 4s2. So this arrangement is not stable. So to make to get the actual electronic configuration with the more stable arrangements of electron, which is, okay, what happened is the one of the electron in orbital 4s is it will move to the orbital 3d. So orbital 3d, it will become more 5 electrons. There are 5 electrons, okay, with the parallel spin, okay, in orbital 3D, and for S, it left one electron after it transferred the electron from the orbital 4s to the 3D. Okay, why it transferred the electron from the orbital 4s to 3D? Because to get the stability of half-filled 3D orbital. So this arrangement is more stable compared to the this one. Okay. Alright, let's see for the copper. Copper, for the expected electronic configurations, okay, you can see that for 3D9 for S2, and it transferred to get the more stable or actual electronic configuration for the copper. It will transfer the electron from the orbital 4s to orbital 3D. So because orbital 3D, it needs only one more electron to achieve the stability of the fully filled d orbital. So that's why it transferred the electron from the orbital 4s to 3D. Then you can see that for the actual electronic configuration for the copper, okay, this is a stable arrangement, d orbital. So why it is anomalous? Okay, because to achieve the stability of the fully filled 3D orbital. Okay. Only these two elements, okay, you have to learn in your syllabus for the anomalous cases. Okay. That's all. Thank you.